Imagine a world where objects can exist in two places at once, where particles communicate instantly across vast distances, and where reality itself seems to bend to the whims of probability. This isn't science fiction. This is the strange and fascinating realm of quantum mechanics. For decades, these mind-bending phenomena were thought to exist only in the microscopic world, confined to the behavior of atoms and subatomic particles. But what if I told you that scientists are now beginning to witness these bizarre quantum effects on a scale we can see with our own eyes? Picture this: a tiny object big enough to hold in your hand, behaving as if it's in multiple states at the same time. It sounds impossible, yet it's happening in labs around the world. These discoveries are not just rewriting the rules of physics, they are challenging our very understanding of reality itself. So, what does it mean for us if the quantum world isn't as separate from our everyday lives as we once thought? What if the same rules that govern the tiniest particles also shape the world we see and touch? These questions aren't just hypothetical, they're at the heart of some of the most groundbreaking experiments being conducted today. Scientists are now observing quantum effects on a macroscopic scale, blurring the line between the microscopic and the visible. From particles that seem to teleport to objects that exist in multiple states simultaneously, these findings are pushing the boundaries of what we thought was possible. They're forcing us to reconsider what we know about the universe and our place within it. In this video, we'll take you on a journey through 25 of the most bizarre quantum effects that scientists are now witnessing on a larger scale. Each one is a window into a world that defies logic and challenges our deepest assumptions about how reality works. You'll discover how these phenomena aren't just confined to the realm of theory. They're being observed in labs, providing tangible evidence of a universe far stranger than we ever imagined. By the end of this exploration, you'll see the world in a whole new light, questioning what's real and what's possible. So, are you ready to dive into the quantum world and uncover the mysteries that lie just beyond the edge of our understanding? Let's begin. Quantum superposition is one of the most perplexing ideas in physics, where particles can exist in multiple states at the same time. For years, this phenomenon was thought to apply only to the subatomic world, far removed from our everyday experience. But recent experiments have turned that assumption on its head. Scientists are now observing quantum superposition in objects large enough to see with the naked eye. Picture this: a tiny crystal or even a microscopic machine behaving as if it's in two places or states simultaneously. It's as if the rules of the quantum world have spilled over into our macroscopic reality, blurring the line between what's possible and what's impossible. One of the most famous metaphors for quantum superposition is Schrödinger's cat, a thought experiment where a cat is placed in a box with a device that could either kill it or leave it unharmed. According to quantum mechanics, until the box is opened, the cat exists in a superposition of both alive and dead states. For decades, this was purely a theoretical exercise, a way to illustrate the strangeness of quantum behavior. But today, scientists are making this bizarre idea a reality. They've created setups where small objects like tiny mirrors or even molecules are placed in states of superposition. These experiments show that superposition isn't just a quirk of the microscopic world. It can manifest in objects we can observe directly. The implications of this are staggering. If an object can exist in multiple states or places at once, what does that mean for our understanding of reality? It challenges the very notion that objects have definite properties until we observe them. This leads us to question whether the universe is as solid and predictable as it seems. or if it's a far more fluid and uncertain place than we've ever imagined. By observing superposition on a larger scale, scientists are not only confirming the weirdness of quantum mechanics, they're also opening the door to new technologies that could revolutionize computing, communication, and even our understanding of time and space. The quantum world, it seems, is no longer confined to the realm of theory. It's becoming a part of our everyday reality. Quantum entanglement is another mind-bending phenomenon that has long fascinated scientists. At its core, entanglement occurs when two or more particles become so deeply connected that the state of one instantly influences the state of the other, no matter how far apart they are. This connection defies our everyday understanding of space and time, as if the particles share an invisible thread that transcends distance. For decades, entanglement was thought to be a feature of the quantum realm, only observable with tiny particles like electrons or photons. But now, researchers are pushing the boundaries, entangling objects on a much larger scale, objects we can actually see and measure. One groundbreaking experiment involved entangling two diamonds separated by a significant distance. Scientists used laser pulses to create a link between the vibrational states of the diamonds, effectively entangling them. Even more astonishing, this entanglement persisted despite the diamonds being physically apart. Another experiment achieved entanglement with small crystals, proving that this quantum connection isn't limited to the microscopic world. These discoveries are reshaping our understanding of entanglement, showing that it's not just a quirky property of atoms, it's a fundamental aspect of reality that can apply to larger systems. What makes these findings so revolutionary is their potential to transform technology. Entanglement lies at the heart of quantum computing, which promises to solve problems far beyond the reach of classical computers. It's also the foundation of quantum communication, enabling ultra-secure data transmission. By entangling larger objects, scientists are moving closer to practical applications that could change the way we process information and interact with technology. But beyond the technological implications, these experiments raise profound questions about the nature of reality. If entanglement can occur over vast distances and in macroscopic objects, what does that say about the interconnectedness of the universe? It's as if the fabric of reality is woven with threads of quantum mystery, waiting to be untangled by those willing to explore the unknown. Quantum tunneling is another astonishing effect that challenges our understanding of physics. Normally, if you roll a ball toward a wall, it bounces back. There's no way it could pass through. But in the quantum world, particles like electrons can do just that. They can tunnel through barriers they seemingly shouldn't be able to penetrate, as if the wall itself becomes momentarily invisible. This phenomenon is a direct result of the probabilistic nature of quantum mechanics, where particles exist in a haze of possibilities until observed. For years, tunneling was thought to be exclusive to the microscopic realm, something only atoms or subatomic particles could experience. But recent experiments have shown that even larger objects, like molecules and tiny mechanical systems, can exhibit this bizarre behavior. Take, for example, a groundbreaking experiment where researchers observed a molecule tunneling through an energy barrier. This wasn't just a fleeting quantum event. It was a measurable, repeatable phenomenon that demonstrated tunneling on a scale we can study in detail. Another experiment involved a nanoscale mechanical device that demonstrated tunneling effects, further blurring the line between the quantum and classical worlds. These discoveries aren't just academic curiosities, they have profound implications for technology. Quantum tunneling is already at the heart of modern electronics, enabling the operation of devices like flash memory and tunnel diodes. But the potential goes even further. Imagine ultra-efficient energy systems where tunneling could enable new forms of energy transfer, bypassing traditional limitations. Or consider its role in space exploration, where tunneling could lead to breakthroughs in propulsion systems, allowing spacecraft to overcome barriers that currently seem insurmountable. The implications for our understanding of the universe are equally staggering. If larger objects can tunnel, what does that say about the boundaries between the quantum and the macroscopic? It's as if the universe itself is hinting at a deeper layer of reality, one where the rules we take for granted start to blur. Could tunneling be a key to unlocking new dimensions of physics, or even a pathway to technologies we can't yet imagine? The possibilities are as vast as the mysteries of the quantum world itself, inviting us to rethink not just how the universe works, but how we might one day harness its secrets. Wave-particle duality is one of the most mind-bending concepts in quantum mechanics, showing that particles like electrons and photons can behave as both particles and waves depending on how you observe them. Think of it like this: if you were to shine light through two narrow slits, it creates an interference pattern on a screen, just like waves in water would. But if you try to catch the light in action, it behaves as discrete particles, hitting the screen in specific spots. This dual nature has been a cornerstone of quantum theory for over a century, but until recently, it was thought to be confined to the tiny world of atoms and subatomic particles. Remarkably, scientists are now seeing this same duality in much larger objects, pushing the boundaries of what we thought was possible. Take, for instance, experiments with molecules composed of hundreds of atoms. Researchers have observed these molecules creating interference patterns, just like light waves would. In one groundbreaking study, scientists used a complex setup to demonstrate wave-like behavior in molecules as large as bucketballs, carbon structures resembling soccer balls. These findings aren't just curiosities. They challenge our fundamental understanding of matter and energy. If something as large as a molecule can act like a wave, what does that mean for the nature of reality itself? It's as if the universe is telling us that the line between the microscopic and the macroscopic isn't as clear as we once believed. The implications of this discovery are profound. For one, it suggests that wave-particle duality might be a universal property of all matter, not just the smallest particles. This could revolutionize fields like materials science, where understanding the wave-like behavior of larger objects could lead to the development of entirely new materials with unprecedented properties. In medicine, it might open the door to advanced imaging techniques that harness the wave nature of larger molecules to see inside the human body with incredible precision. And in technology, it could pave the way for quantum computing systems that operate on a much larger scale than currently imagined. But beyond the practical applications, wave-particle duality raises deeper philosophical questions. If matter can behave as both a particle and a wave, what does that say about the nature of reality? Are we missing something fundamental about how the universe works? These questions remind us that even as we push the boundaries of science, the mysteries only seem to deepen, inviting us to explore further and rethink our place in the cosmos. As we continue to uncover these bizarre quantum effects in larger systems, one thing is clear: the quantum world is far stranger and more interconnected than we ever imagined. Quantum coherence, the phenomenon where particles synchronize their behavior, is not just a quirky feature of the quantum world. It's now being observed in the most unexpected places: living organisms. Take photosynthesis, for example. Plants, algae, and some bacteria have evolved an incredibly efficient way to convert sunlight into energy, and scientists believe quantum coherence plays a key role. Inside the cells of these organisms, light energy is captured by molecules called chlorophyll, which then transfer this energy to specific sites where it's converted into chemical energy. What's astonishing is that this energy transfer seems to happen with almost perfect efficiency, a feat that classical physics struggles to explain. Researchers have discovered that during photosynthesis, particles involved in energy transfer exhibit wave-like behavior, allowing them to explore multiple pathways simultaneously. This quantum coherence ensures that the energy takes the most efficient route, minimizing losses. In other words, plants might be harnessing quantum mechanics to optimize their survival, a concept that blurs the line between biology and physics. Experiments using ultrafast laser pulses have revealed that this coherence persists even at room temperature, challenging the assumption that quantum effects are too fragile to exist outside controlled laboratory conditions. The implications of this discovery extend far beyond plants. Could other living organisms also be tapping into quantum mechanics? Some scientists speculate that birds might use quantum coherence in their navigation systems, allowing them to sense Earth's magnetic field with incredible precision. Even human biology might not be immune to these effects. Enzymes, the molecular machines that drive countless chemical reactions in our bodies, are now being studied for signs of quantum tunneling, a process where particles pass through energy barriers as if they weren't there. This could explain how certain biochemical reactions occur at speeds that classical physics can't account for. If quantum coherence is indeed a widespread phenomenon in biology, it could revolutionize our understanding of life itself. It suggests that nature has found ways to exploit the bizarre rules of the quantum world to gain a survival advantage. For scientists, this opens up exciting possibilities, from designing more efficient solar panels inspired by photosynthesis to developing new medical treatments that harness quantum effects. But it also raises profound questions. How did life evolve to harness these effects? Are there other quantum tricks hidden in the natural world waiting to be uncovered? As we continue to explore this frontier, one thing is clear: the quantum world and the living world are far more intertwined than we ever imagined. Imagine the fabric of space itself as a bubbling cauldron of energy, where particles flicker in and out of existence in a dance of uncertainty. This is the quantum vacuum, and its fluctuations, once thought to be confined to the tiniest scales, are now showing up in ways we can see with our own eyes. Scientists have discovered that these seemingly random fluctuations can have profound effects, even shaping the universe on the largest scales. Take the formation of galaxies, for instance. The early universe was a nearly uniform sea of matter and energy, but tiny quantum fluctuations created slight variations in density. Over billions of years, these variations grew under the pull of gravity, giving rise to the vast cosmic structures we observe today. In a very real sense, the galaxies, stars, and planets we see are the amplified echoes of quantum jitters from the dawn of time, but it doesn't stop there. Quantum fluctuations are now being detected in experiments that involve everyday objects, not just subatomic particles. Researchers have observed these fluctuations in systems like tiny mechanical oscillators, devices that vibrate at specific frequencies. These oscillators, though small by everyday standards, are massive compared to the scale where quantum effects usually play out. Yet, they exhibit behavior that can only be explained by the influence of quantum fluctuations. This suggests that the boundary between the quantum and macroscopic worlds is far blurrier than we once thought. What's even more fascinating is how these fluctuations might affect the behavior of objects we interact with daily. For example, the very stability of matter itself could be influenced by these tiny shifts in the quantum field. While the effects are too subtle to notice in most situations, they could play a role in phenomena like friction, material strength, or even the way light interacts with surfaces. This opens up a world of possibilities for new technologies. Imagine materials engineered to harness quantum fluctuations for unprecedented properties. Think ultra-efficient energy transfer or devices that operate with near-perfect precision. The implications for our understanding of the universe are equally staggering. If quantum fluctuations can shape galaxies and influence macroscopic objects, they might also hold clues to some of the deepest mysteries in physics, like the nature of dark energy or the unification of quantum mechanics and gravity. As we continue to probe these effects, we're not just uncovering the hidden mechanics of reality, we're redefining what it means to observe the quantum world. It's a reminder that even in the most ordinary moments, the universe is humming with the extraordinary. Picture a state of matter where countless atoms lose their individuality and merge into a single, unified quantum entity. This is the essence of a Bose-Einstein condensate, a phenomenon first predicted nearly a century ago, but only realized in the lab in the mid-1990s. In this exotic state, atoms chilled to temperatures just above absolute zero synchronize their behavior, forming what's often described as a superatom. Unlike gases, liquids, or solids, Bose-Einstein condensates obey the rules of quantum mechanics on a macroscopic scale, creating a playground for exploring the strange and counterintuitive properties of the quantum world. What makes these condensates so remarkable is not just their otherworldly nature, but also the way they challenge our understanding of scale. Initially, scientists created Bose-Einstein condensates using tiny clouds of atoms, but recent breakthroughs have pushed the boundaries. Researchers are now producing these states in larger systems, involving more particles and occupying more space. This expansion brings quantum effects into a realm where they're visible to the naked eye, blurring the line between the microscopic and the macroscopic. The potential applications of this research are nothing short of transformative. In the field of quantum computing, Bose-Einstein condensates could serve as the foundation for highly stable qubits, the building blocks of quantum processors. Their ability to maintain coherence over longer periods could address one of the biggest challenges in quantum computing, decoherence, which causes qubits to lose their quantum state. Beyond computing, these condensates hold promise for ultra-precise sensors capable of detecting minute changes in gravity, magnetic fields, or even the passage of time. Such devices could revolutionize everything from navigation systems to medical imaging, but the implications go even further. By studying Bose-Einstein condensates, scientists are gaining insights into fundamental questions about the nature of matter and the universe. For instance, these systems mimic the behavior of exotic phenomena like superconductivity and superfluidity, offering a laboratory for testing theories that would otherwise be impossible to explore. They also provide a testing ground for ideas about quantum entanglement and how it might scale up to larger systems, potentially shedding light on the quantum nature of reality itself. As we continue to push the limits of what's possible with Bose-Einstein condensates, we're not just unlocking new technologies, we're rewriting the rules of what matter can do. It's a testament to the power of quantum mechanics and a reminder that even the coldest, most controlled environments can reveal the universe's deepest mysteries. The observer effect is one of the most mind-bending ideas in quantum mechanics, revealing that the very act of measuring a system can alter its state. At its core, this principle suggests that particles like electrons or photons don't have definite properties until they're observed. This isn't just a quirk of tiny particles, it's a fundamental feature of reality that's now being observed in larger and more complex systems, challenging our understanding of the universe. Imagine a world where simply looking at something changes its behavior. This isn't science fiction. It's a phenomenon scientists are actively investigating in labs around the globe. In the quantum realm, the observer effect is famously illustrated by the double-slit experiment, where particles act like waves until they're measured, at which point they behave like discrete particles. But what happens when we scale this up? Recent experiments have demonstrated similar effects in objects much larger than atoms, from molecules to tiny mechanical devices. For instance, researchers have observed that measuring the position of a tiny vibrating membrane can influence its motion, effectively bringing quantum behavior into the macroscopic world. These findings blur the line between the quantum and classical realms, forcing us to rethink the boundaries of where quantum mechanics applies. The philosophical implications of the observer effect are profound. If observation can alter reality, does that mean the universe only takes shape when we observe it? This idea aligns with interpretations of quantum mechanics like the Copenhagen interpretation, which suggests that quantum systems exist in a superposition of states until measured. However, it also raises questions about the nature of consciousness and its role in shaping reality. Are we, as observers, active participants in the universe's unfolding, or is the observer effect simply a consequence of measurement tools interacting with systems? These questions delve into the heart of what it means to exist in a quantum world. Moreover, the observer effect challenges our everyday understanding of reality. We're used to thinking of the world as stable and objective, independent of our observations. But quantum mechanics suggests that at a fundamental level, reality is dynamic and responsive, shaped by the act of measurement. This has implications not just for physics, but for how we perceive ourselves and our place in the universe. It's a reminder that science isn't just about discovering what's out there. It's also about understanding how we influence and interact with the world around us. As we continue to explore the observer effect in larger systems, we're not just pushing the boundaries of physics, we're also confronting profound questions about the nature of reality itself. Whether through groundbreaking experiments or philosophical inquiry, this phenomenon invites us to reconsider what it means to observe, to measure, and to exist in a universe where the act of looking can change the very fabric of what we see. Quantum decoherence is the process that explains why the bizarre behavior of quantum systems doesn't typically show up in our everyday world. In essence, it's the reason why a cat isn't both alive and dead at the same time, even though quantum particles can exist in multiple states simultaneously. Decoherence occurs when a quantum system interacts with its environment, causing its unique quantum properties like superposition and entanglement to fade away. This interaction produces a kind of quantum noise that effectively collapses the system into a single classical state. It's like trying to hear a whisper in a crowded room. The delicate quantum information gets drowned out by the surrounding chaos. But what's truly fascinating is that scientists are now observing decoherence in larger and more complex systems than ever before. Traditionally, decoherence was studied in particles or atoms, where environmental interactions are hard to avoid. However, recent experiments have pushed this phenomenon into the macro scale, using objects like tiny mirrors, superconducting circuits, and even microscopic beads suspended in air. For example, researchers have demonstrated that even a small mechanical resonator, visible to the naked eye, can exhibit quantum coherence, but only for a fleeting moment before decoherence takes over. These experiments are helping us understand the boundary between the quantum and classical worlds, showing that decoherence isn't just a small-scale effect but a universal process. The role of decoherence in the transition from quantum to classical physics is profound. It provides a possible explanation for why we don't see quantum weirdness in larger objects, even though they're ultimately made of quantum particles. Essentially, decoherence acts as a bridge between the probabilistic rules of quantum mechanics and the deterministic laws of classical physics. It doesn't just explain the disappearance of quantum effects, it also highlights the critical role of the environment in shaping physical reality. This idea challenges the notion of a purely objective universe, suggesting that the environment itself acts as a kind of observer, influencing the behavior of quantum systems. Exploring decoherence on a macro scale also has practical implications. Understanding how and why quantum states collapse could lead to breakthroughs in quantum computing, where maintaining coherence is essential for processing information. It also raises questions about the nature of reality itself. If decoherence can erase quantum effects in larger systems, does that mean the universe has a built-in mechanism for favoring classical behavior? Or is it simply a matter of scale and complexity, with quantum effects becoming harder to detect as systems grow larger? These questions push us to rethink not just the mechanics of the universe, but also the very nature of existence. Quantum interference, once thought to be confined to the realm of tiny particles, is now making waves in the macro world. This phenomenon occurs when a particle seems to interfere with itself, creating patterns that defy classical intuition. For instance, in the famous double-slit experiment, particles like electrons or photons create an interference pattern when passing through two slits, as if they're both a particle and a wave. Traditionally, this behavior was only observed in microscopic systems, but recent breakthroughs have shown that even larger objects can exhibit these quantum quirks. Sensors made of tiny, vibrating membranes or even small mechanical resonators have demonstrated interference effects, blurring the line between the quantum and classical worlds. These experiments are not just scientific curiosities, they're opening doors to revolutionary technologies. The implications of macroscopic quantum interference are enormous, particularly in the field of precision measurement. Interference patterns are incredibly sensitive to external forces, making them ideal for detecting minute changes in motion, gravity, or even the presence of nearby objects. For example, researchers are developing quantum sensors that use interference to measure gravitational waves with unprecedented accuracy. These sensors could also detect tiny shifts in the Earth's crust, potentially providing early warnings for earthquakes. The same principle is being applied to navigation systems, where quantum interference could create ultra-precise gyroscopes, enabling aircraft or submarines to navigate without relying on external signals like GPS. The ability to harness interference on a larger scale could transform industries reliant on precision, from medical imaging to environmental monitoring. Beyond practical applications, macroscopic quantum interference challenges our understanding of reality. If objects large enough to be seen with the naked eye can exhibit interference, it suggests that quantum mechanics isn't just a theory for the microscopic world, it's a fundamental part of the universe at all scales. This realization forces us to reconsider the nature of matter and motion, raising questions about the limits of classical physics. It also hints at the possibility of creating hybrid systems that combine quantum and classical properties, potentially leading to new materials or technologies that blur the boundaries between the two worlds. As we continue to push the limits of quantum interference, we're not just exploring new scientific frontiers, we're redefining what's possible in the realm of physics and engineering. Quantum teleportation, a process that sounds like something out of science fiction, is very much a reality, and it's not limited to the microscopic world anymore. At its core, quantum teleportation involves transferring the quantum state of one particle to another, instantaneously and without traveling through the space in between. This isn't about moving physical objects, but rather about transmitting information in a way that defies classical physics. For years, this phenomenon was only achieved with particles like photons or atoms, but recent experiments have pushed the boundaries, demonstrating teleportation in larger systems, including clouds of atoms and even solid-state devices. These advancements are not just scientific milestones, they're paving the way for transformative technologies. One of the most exciting implications of scaled-up quantum teleportation is its potential to revolutionize communication. Traditional methods of transmitting data rely on signals that travel through cables or the air, which are limited by the speed of light and prone to interference. Quantum teleportation, on the other hand, allows information to be transferred instantaneously, regardless of distance. This could lead to the development of quantum networks that are virtually unhackable, as any attempt to intercept the data would disrupt the quantum state, alerting users to the breach. Imagine a future where sensitive information, from financial transactions to military communications, is transmitted with absolute security. The impact on global communications would be nothing short of revolutionary. But the applications don't stop there. Quantum teleportation could also play a crucial role in the development of quantum computers. These machines rely on qubits, which can exist in multiple states simultaneously, allowing them to perform complex calculations far beyond the reach of classical computers. However, qubits are extremely fragile and can lose their quantum state through interactions with their environment. Teleportation offers a way to move quantum information between qubits without exposing it to these risks, potentially overcoming one of the biggest challenges in quantum computing. This could accelerate the creation of powerful quantum systems capable of solving problems that are currently intractable, from simulating molecular interactions for drug discovery to optimizing large-scale logistics networks. Scaling quantum teleportation to larger systems also raises profound questions about the nature of reality and the limits of classical physics. The phenomenon relies on a property called entanglement, where particles become so deeply connected that the state of one instantly influences the state of another, even across vast distances. Einstein famously referred to this as spooky action at a distance, and its implications are still being explored as scientists demonstrate teleportation in increasingly complex systems. We're forced to grapple with the idea that the universe operates in ways that defy our everyday intuition. This isn't just about advancing technology, it's about deepening our understanding of the fundamental principles that govern existence. As research in this field continues, the possibilities seem almost limitless. From secure global communication networks to the next generation of computing, quantum teleportation is poised to reshape the technological landscape. And while the idea of teleporting objects or people remains firmly in the realm of science fiction, the ability to transmit information instantaneously is a reality that's already within our grasp. This is more than just a scientific achievement. It's a glimpse into a future where the boundaries of space and time are no longer constraints but opportunities. Time, a concept so fundamental to our existence, might not be as straightforward as it seems. Recent experiments are challenging the classical idea of time as a continuous, smooth flow, suggesting instead that it could have a quantum nature. This means time might be made up of discrete, indivisible units much like particles. Imagine time not as a river but as a series of tiny droplets, each representing the smallest possible increment of time. This idea, while abstract, is rooted in the principles of quantum mechanics, where everything seems to come in discrete packets from energy to matter. If time itself behaves this way, it would fundamentally alter our understanding of the universe. One of the most fascinating aspects of this theory is the idea of chronons, hypothetical quanta of time. Just as photons are the smallest units of light, chronons would represent the smallest units of time. Studies in quantum gravity, a field that seeks to unify quantum mechanics with general relativity, suggests that at the smallest scales, time might not flow smoothly but instead jump from one chronon to the next. This could explain why certain phenomena at the quantum level seem to defy our everyday experience of time. For instance, particles can appear to exist in multiple states simultaneously or jump between states without passing through intermediate ones, behavior that aligns with a discontinuous view of time. The implications of this are profound. If time is quantized, it would mean that our perception of its continuous flow is an illusion, a result of scales too large for us to detect the individual ticks of the universe's clock. This could also provide new insights into the nature of black holes and the early moments of the Big Bang, where the fabric of space-time is stretched to its limits. It might even offer clues about the unification of the four fundamental forces of nature, a goal that has eluded physicists for decades. The quantum nature of time could be the key to unlocking some of the universe's deepest mysteries. Moreover, this idea challenges our philosophical understanding of time. If time is made up of discrete units, what does that mean for cause and effect, the very foundation of how we understand the world? In a continuous time framework, cause precedes effect in a clear, linear fashion. But in a quantized time model, the relationship between cause and effect might become more complex, opening the door to entirely new ways of thinking about reality. It raises questions about free will, determinism, and the nature of existence itself. While the quantum nature of time is still a theoretical concept, experiments are beginning to test its validity. Cutting-edge research in quantum optics and atomic clocks is pushing the boundaries of how precisely we can measure time, bringing us closer to detecting these hypothetical chronons. If confirmed, this discovery would not only revolutionize physics but also our everyday lives. Technologies like GPS, which rely on precise timekeeping, could become even more accurate, while new innovations in quantum computing and communication might emerge from this deeper understanding of time's true nature. This exploration of time's quantum nature reminds us that the universe is far stranger and more wondrous than we often realize. It challenges us to rethink long-held assumptions and embrace the possibility that even the most familiar concepts might have hidden layers waiting to be uncovered. As we continue to probe the mysteries of time, we're not just learning more about the cosmos, we're also learning more about ourselves and our place within it. Quantum gravity represents one of the most profound challenges in modern physics, seeking to bridge the gap between the microscopic world of quantum mechanics and the vast cosmic scale of general relativity. While quantum mechanics governs the behavior of particles at the smallest scales, general relativity describes the force of gravity and the structure of spacetime on a grand scale. Yet these two theories, despite their individual successes, seem incompatible when combined. Quantum gravity aims to resolve this conflict, offering a unified framework that could explain everything from the behavior of subatomic particles to the dynamics of black holes and the origins of the universe. One of the key ideas in quantum gravity is that spacetime itself might have a quantum structure. Instead of being a smooth, continuous fabric, spacetime could be made up of tiny, discrete units akin to pixels in a digital image. These units, often referred to as spacetime foam, would be unimaginably small, existing at the Planck scale, which is about 1/trillionth of a trillionth of the diameter of an atomic nucleus. At this scale, the very fabric of reality might fluctuate wildly, with spacetime bubbling and churning in a chaotic dance of quantum uncertainty. Scientists are now exploring ways to observe these quantum gravitational effects on larger scales, pushing the boundaries of what we thought was possible. For example, experiments with ultra-precise atomic clocks are attempting to detect tiny variations in the flow of time caused by quantum fluctuations in spacetime. Similarly, observations of distant cosmic phenomena, such as gamma-ray bursts and gravitational waves, might reveal subtle signatures of quantum gravity. These efforts are not just about proving a theory, they're about unlocking a deeper understanding of the universe and how it operates at every level. The implications of quantum gravity extend far beyond theoretical physics. If confirmed, it could revolutionize our understanding of spacetime, offering new insights into the nature of black holes, the Big Bang, and even the possibility of other dimensions. It might also pave the way for new technologies, from advanced quantum computers to novel methods of space travel. But perhaps most importantly, quantum gravity represents a fundamental shift in how we perceive reality, challenging us to rethink the very nature of existence. By studying quantum gravity on a macro scale, scientists are not just probing the limits of our current knowledge, they're venturing into uncharted territory, where the rules of the universe might be rewritten. This exploration is a testament to human curiosity and our relentless drive to understand the cosmos. As we continue to push the boundaries of science, we're reminded that the universe is full of mysteries waiting to be uncovered, and that every discovery brings us one step closer to unraveling the true fabric of reality. Quantum chaos, once a concept confined to the microscopic realm, is now revealing its presence in systems we can see and measure. This phenomenon occurs when the behavior of quantum particles becomes unpredictable and highly sensitive to initial conditions, much like the chaos seen in classical systems like weather patterns or fluid dynamics. What's astonishing is that scientists are now observing these chaotic quantum effects on a macroscopic scale, bridging the gap between the quantum and classical worlds. One striking example is the study of complex quantum systems, such as certain types of superconducting circuits or even large molecules. In these systems, the interplay of quantum mechanics and chaos leads to behaviors that are both fascinating and unpredictable. For instance, the energy levels of these systems can arrange themselves in patterns that resemble the randomness of a drumbeat, a phenomenon known as quantum scarring. This discovery has opened up new avenues for understanding how chaos manifests in the quantum realm and how it influences larger, visible systems. These findings aren't just academic curiosities, they have practical applications, particularly in the fields of cryptography and secure communication. Quantum chaos can be harnessed to create highly secure encryption methods. Because chaotic systems are inherently unpredictable, they can generate encryption keys that are virtually impossible to crack using conventional methods. This makes them ideal for protecting sensitive information in an era where cybersecurity is more critical than ever. Researchers are also exploring how quantum chaos can enhance the security of quantum communication networks, which rely on the principles of quantum entanglement to transmit data securely over vast distances. Beyond cryptography, the study of quantum chaos is shedding light on the fundamental nature of reality. It challenges our understanding of how order and disorder coexist in the universe and how the transition from quantum to classical behavior occurs. By studying chaos in visible quantum systems, scientists are uncovering clues about the underlying principles that govern everything from the smallest particles to the largest cosmic structures. This exploration of quantum chaos is a reminder that the boundaries between the quantum and classical worlds are not as rigid as we once thought. As we continue to investigate these phenomena, we're not only advancing our understanding of the universe, but also unlocking new tools to shape the future of technology and communication. The journey into the chaotic heart of quantum mechanics is just beginning, and the discoveries ahead promise to be as unpredictable as the systems we're studying. The quantum Zeno effect, named after the ancient Greek philosopher Zeno of Elea, is a fascinating phenomenon where the act of frequent observation can effectively freeze a system state. In the quantum world, particles are constantly in a state of flux, but if you observe them often enough, they seem to remain unchanged, as if held in place by the observer's gaze. This effect, once thought to apply only to tiny particles like atoms or electrons, is now being observed in larger, more complex systems, challenging our understanding of where the quantum world ends and the classical world begins. One recent experiment demonstrated this effect using a macroscopic object, a tiny mechanical resonator. By repeatedly measuring its position, researchers were able to prevent it from moving, effectively freezing its state. This discovery is groundbreaking because it shows that the quantum Zeno effect isn't limited to the microscopic scale. It also opens up exciting possibilities for stabilizing larger systems, which could have profound implications for quantum computing and other advanced technologies. In quantum computing, for example, maintaining the stability of qubits, the basic units of quantum information, is a major challenge. Qubits are highly sensitive to their environment and can easily lose their quantum properties, a problem known as decoherence. By applying the quantum Zeno effect, scientists could potentially freeze qubits in their desired states, reducing errors and improving the reliability of quantum computers. This could accelerate the development of quantum technologies that are faster and more powerful than anything we have today. Another promising application is in the field of precision measurement. By using the quantum Zeno effect to stabilize systems, researchers could create ultra-sensitive sensors capable of detecting minute changes in physical quantities like temperature, pressure, or magnetic fields. These sensors could revolutionize fields ranging from medical diagnostics to environmental monitoring, offering unprecedented accuracy and sensitivity. The implications of observing the quantum Zeno effect on a larger scale extend beyond practical applications. They also deepen our understanding of the fundamental nature of reality. How does observation influence the behavior of objects, and where do we draw the line between the quantum and classical worlds? These questions challenge our intuition and push the boundaries of what we thought was possible in physics. As we continue to explore this phenomenon, we're not just unlocking new technologies, we're uncovering the intricate dance between observation and reality itself. Quantum entropy, a concept that describes the chaos or unpredictability within a quantum system, has traditionally been associated with particles like electrons or photons. However, recent research has revealed that this phenomenon is not confined to the microscopic realm. It also plays a role in larger, everyday objects. Scientists are now studying how quantum entropy affects systems like tiny mechanical oscillators and even certain biological molecules, shedding new light on the boundary between quantum and classical physics. One of the most intriguing aspects of this discovery is its potential impact on thermodynamics, the science of heat and energy transfer. In classical thermodynamics, entropy is often associated with wasted energy. The more disordered a system, the less efficient it becomes. But in the quantum world, entropy takes on a different character. It's not just a measure of disorder, it's also a window into the system's quantum states. By understanding how quantum entropy behaves in larger systems, researchers are uncovering new ways to harness energy more efficiently. For instance, in the field of energy storage, quantum entropy could revolutionize the design of batteries and capacitors. Traditional energy storage devices lose efficiency as entropy increases, but by controlling quantum entropy, scientists might be able to create devices that maintain high efficiency even under extreme conditions. Imagine a battery that doesn't degrade over time or a capacitor that can store energy with minimal loss. These advancements could transform industries from consumer electronics to renewable energy. Quantum entropy also has implications for understanding the fundamental laws of physics. The second law of thermodynamics states that entropy in an isolated system always increases, leading to the inevitable heat death of the universe. But quantum entropy introduces a new layer of complexity. In some cases, quantum effects can temporarily reduce entropy, effectively reversing the arrow of time on a small scale. This doesn't violate the second law, but it does challenge our understanding of how entropy operates in the quantum realm, opening up new questions about the nature of time and energy. Another exciting area of research involves biological systems. Some scientists are exploring whether quantum entropy plays a role in processes like photosynthesis or enzyme activity. In these systems, efficiency is key, and even small improvements could have significant consequences. If quantum entropy can be harnessed in biological contexts, it could lead to breakthroughs in medicine, agriculture, and environmental science, offering new ways to optimize natural processes. As we continue to study quantum entropy in larger systems, we're not just expanding our understanding of physics, we're unlocking new possibilities for technology and energy. This research bridges the gap between quantum mechanics and classical thermodynamics, offering a glimpse into a future where energy is used more efficiently, technology is more reliable, and the fundamental laws of physics are understood in greater depth. The exploration of quantum entropy is a testament to the incredible potential of blending quantum theory with real-world applications, pushing the boundaries of what we thought was possible. Quantum jumps, the sudden transitions of particles between energy levels, have long been a hallmark of the quantum world. These instantaneous shifts, once thought to occur only at the atomic or subatomic scale, are now being observed in larger, more complex systems, a discovery that's reshaping our understanding of quantum mechanics. Researchers have successfully tracked quantum jumps in superconducting circuits and even in tiny mechanical resonators, systems that are thousands of times larger than individual atoms. This breakthrough not only challenges the boundaries of quantum physics, but also opens up exciting possibilities for practical applications, particularly in quantum computing. In the realm of quantum computing, controlling quantum jumps could be the key to building more stable and efficient systems. Traditional computers rely on bits that exist in one of two states, 0 or 1, but quantum computers use qubits, which can exist in multiple states simultaneously thanks to the principle of superposition. However, qubits are notoriously fragile, often losing their quantum state due to tiny environmental disturbances. By precisely monitoring and controlling quantum jumps, scientists could develop ways to stabilize qubits, significantly reducing errors and improving the reliability of quantum computations. One promising approach involves using quantum jumps as a feedback mechanism. In this method, researchers continuously monitor a qubit state and detect when it's about to undergo an unwanted jump. By applying corrective measures in real time, they can prevent the qubit from losing its quantum information. This technique, known as quantum error correction, is essential for scaling up quantum computers to handle complex tasks in fields like cryptography, drug discovery, and optimization problems. Beyond computing, quantum jumps are also being explored for their potential in sensing technologies. Because these jumps are incredibly sensitive to external influences, they could be used to create ultra-precise sensors for detecting minute changes in magnetic fields, temperature, or even gravitational waves. Such sensors could have applications in medical imaging, geological exploration, and even the search for dark matter, offering unprecedented levels of precision and accuracy. The study of macroscopic quantum jumps also provides deeper insights into the nature of quantum mechanics itself. For decades, scientists have debated whether quantum behavior could ever be observed in larger objects, or if it's strictly limited to the microscopic world. The fact that quantum jumps can now be seen in systems that are visible to the naked eye suggests that the quantum realm is far more pervasive than previously thought. This raises intriguing questions about the fundamental nature of reality. Could quantum effects play a role in the behavior of everyday objects, and if so, to what extent? As we continue to explore the implications of macroscopic quantum jumps, we're not just pushing the boundaries of science, we're paving the way for transformative technologies. From more powerful quantum computers to groundbreaking sensors, the ability to harness and control these phenomena could revolutionize multiple industries. The observation of quantum jumps in larger systems is a remarkable reminder that the quantum world is full of surprises, and its secrets are only just beginning to unfold. Quantum noise, the subtle yet persistent fluctuations that arise from the inherent randomness of quantum systems, is no longer confined to the microscopic world. Scientists are now observing and studying this phenomenon in larger, more visible objects, revealing how it impacts everything from measurement precision to the development of cutting-edge technologies. This noise, which emerges from the probabilistic nature of quantum mechanics, introduces a fundamental limit to how accurately we can measure and control physical systems. Even in objects that appear stable to the naked eye, the quantum world's chaotic undercurrents are at play, subtly influencing their behavior. One of the most striking examples of quantum noise's effects can be seen in the field of precision measurement. Consider the development of atomic clocks, devices that rely on the oscillations of atoms to keep time with extraordinary accuracy. While these clocks are marvels of engineering, they are ultimately constrained by quantum noise. The random fluctuations in the atom's energy levels introduce tiny uncertainties in the clock's measurements, limiting how precise they can become. This might seem like a minor issue, but in contexts like GPS navigation, where timing accuracy is critical, even the smallest errors can have significant consequences. Quantum noise also poses challenges in the development of quantum sensors, devices designed to detect incredibly faint signals, such as gravitational waves or magnetic fields. These sensors operate at the edge of quantum sensitivity, where the slightest disturbance can overwhelm the signal they're trying to measure. Quantum noise, being an ever-present factor, creates a background static that can obscure the data. Researchers are working on innovative techniques to mitigate this noise, such as using quantum entanglement to amplify signals while suppressing unwanted fluctuations. But the battle against noise remains a central focus in this field. Interestingly, quantum noise isn't just a problem to be solved, it's also a source of potential insight. By studying how noise behaves in larger systems, scientists can gain a deeper understanding of the boundary between the quantum and classical worlds. For instance, experiments with macroscopic objects like tiny mechanical oscillators have shown that quantum noise doesn't disappear as objects grow larger. Instead, it becomes more complex, influenced by factors like temperature and material properties. This suggests that quantum effects might play a more significant role in our everyday world than we've previously realized. The study of quantum noise also has practical implications for emerging technologies. In quantum computing, for example, noise is a major obstacle to achieving stable and reliable operations. Qubits, the building blocks of quantum computers, are highly susceptible to noise, which can cause errors and disrupt computations. To overcome this, researchers are developing error-correcting codes and noise reduction techniques that could one day make quantum computers robust enough for real-world applications. Similarly, in fields like telecommunications, understanding and controlling quantum noise could lead to more secure and efficient data transmission methods. As we continue to explore the impact of quantum noise on larger systems, we're not just pushing the limits of technology, we're also uncovering new layers of complexity in the quantum world. This phenomenon, once thought to be a minor quirk of tiny particles, is proving to be a pervasive and influential force, shaping the behavior of objects across a wide range of scales. By learning to harness and control quantum noise, we could unlock new possibilities in precision measurement, computing, and beyond, ultimately bridging the gap between the quantum and classical realms in ways that were once unimaginable. Quantum phase transitions, the dramatic shifts in a system state driven purely by quantum fluctuations rather than thermal energy, are no longer confined to the realm of tiny particles. Scientists are now observing these transitions in larger, macroscopic systems, uncovering a fascinating interplay between quantum mechanics and the everyday world. Unlike classical phase transitions such as water turning to ice, which require changes in temperature, quantum phase transitions occur at absolute zero, where thermal energy is absent. Instead, these transitions are triggered by variations in external parameters like pressure or magnetic fields, which alter the system's quantum state. This discovery is revolutionizing our understanding of how materials behave under extreme conditions. One of the most intriguing areas where quantum phase transitions are being studied is in exotic materials known as quantum critical systems. These materials exist at the edge of stability, where even the slightest change in external conditions can trigger a dramatic shift in their properties. For instance, certain superconductors, materials that conduct electricity with zero resistance, exhibit quantum phase transitions when exposed to strong magnetic fields. At a critical field strength, the system transitions from a superconducting state to a normal state, revealing the underlying quantum mechanics that govern this change. By studying these transitions, researchers can uncover the fundamental principles that enable superconductivity, potentially paving the way for new technologies like ultra-efficient power grids or quantum computers. Another fascinating example is found in heavy fermion materials, where electrons behave as if they are hundreds of times more massive than normal. These materials often exhibit quantum phase transitions when subjected to pressure or magnetic fields, transitioning between states with vastly different magnetic and electrical properties. These transitions provide a window into the complex ways electrons interact in these materials, shedding light on phenomena like magnetism and electrical conductivity. Understanding these processes could lead to the development of new materials with tailored properties for advanced applications. The study of quantum phase transitions in larger systems also has profound implications for our understanding of the universe. For example, the behavior of matter near a quantum critical point, the precise conditions where a phase transition occurs, shares striking similarities with the early moments of the Big Bang. By creating and analyzing these conditions in the lab, scientists can test theories about the fundamental forces that shape the cosmos. This connection between the microscopic and the cosmic highlights the far-reaching importance of quantum phase transitions in both science and technology. As researchers continue to explore these transitions in macroscopic systems, they're not only deepening our understanding of quantum mechanics, but also opening new doors for innovation. From designing materials with unprecedented properties to unraveling the mysteries of the universe, The study of quantum phase transitions is a testament to the profound and often unexpected ways the quantum world influences our lives. By pushing the boundaries of what we thought was possible, scientists are revealing a universe where the rules of quantum mechanics shape everything, from the tiniest particles to the largest structures in existence. Quantum time crystals are one of the most mind-bending discoveries in modern physics, defying our conventional understanding of both time and matter. Unlike traditional crystals, which have repeating patterns in space, time crystals exhibit a repeating pattern in time. This means their structure oscillates or cycles without any external energy input, effectively breaking the symmetry of time and creating a form of perpetual motion. First theorized in 2012 by Nobel laureate Frank Wilczek, time crystals were initially met with skepticism as they seemed to challenge the laws of thermodynamics. However, in recent years, scientists have successfully created these exotic structures, not just in microscopic systems but on a macroscopic scale, opening up a world of possibilities. One of the key breakthroughs in creating time crystals involves using systems of trapped ions or carefully arranged atoms in a diamond lattice. By applying precise laser pulses or magnetic fields, researchers can induce these systems to oscillate in a stable, repeating pattern indefinitely, even at the lowest possible energy state. This ability to maintain such rhythmic behavior without energy loss is what makes time crystals so extraordinary. They're not violating the laws of physics, but rather exploiting the unique properties of quantum mechanics to achieve something that seems impossible in the classical world. The implications of time crystals are profound, particularly in the field of quantum computing. One of the biggest challenges in quantum computing is maintaining coherence, keeping qubits, the basic units of quantum information, stable and synchronized for long enough to perform calculations. Time crystals could provide a solution by acting as highly stable clocks or synchronizers for qubits, helping to reduce errors and enhance computational efficiency. Their robustness and predictability make them ideal candidates for improving the reliability of quantum systems, potentially accelerating the development of practical quantum computers. Beyond computing, time crystals could also revolutionize our understanding of fundamental physics. They provide a new way to explore phenomena like symmetry breaking and the nature of time itself. By studying these structures, scientists can test theories about how time operates at the quantum level, offering insights that could reshape our understanding of the universe. The ability to create time crystals on a macroscopic scale also bridges the gap between the quantum world and the everyday, bringing abstract concepts into tangible reality. As research into time crystals continues, the potential applications are only beginning to emerge. From advancing quantum technologies to unraveling the mysteries of time, these structures represent a new frontier in science. By pushing the boundaries of what we thought was possible, physicists are not only expanding our knowledge but also paving the way for innovations that could transform technology and deepen our connection to the fabric of reality. The quantum Hall effect is a striking example of how quantum mechanics can manifest in unexpected ways, even in larger systems. This phenomenon occurs when electrons are confined to a two-dimensional plane and subjected to a strong magnetic field. Under these conditions, the electrons don't behave as they normally would. Instead, they form discrete energy levels called Landau levels. What's remarkable is that the electrical resistance of the system becomes quantized, meaning it takes on specific, unchanging values that are incredibly precise. These values are determined by fundamental constants of nature, like the Planck constant and the electron charge, making the quantum Hall effect a cornerstone of precision measurement. Historically, the quantum Hall effect was first observed in extremely small, carefully prepared samples at ultra-low temperatures. but recent advancements have shown that this effect can also occur in larger systems, even at higher temperatures. Researchers have discovered ways to create conditions where the quantum Hall effect emerges in materials like graphene and other two-dimensional structures. This breakthrough not only broadens our understanding of quantum phenomena, but also makes it possible to harness these effects for practical applications. One of the most significant uses is in the field of metrology, the science of measurement. Because the quantized resistance values are so stable and precise, they serve as a universal standard for electrical resistance. This has led to the development of highly accurate measurement tools used in industries ranging from electronics to aerospace. The quantum Hall effect also plays a crucial role in advancing our understanding of topological phases of matter. These are states of matter where the properties are robust against external disturbances, thanks to their underlying geometric and topological characteristics. This robustness makes them incredibly valuable for developing fault-tolerant materials and devices, particularly in the realm of quantum computing. By studying how the quantum Hall effect operates in larger systems, scientists are uncovering new ways to design materials that can maintain their properties under real-world conditions, paving the way for more reliable and efficient technologies. Another fascinating aspect of the quantum Hall effect is its connection to the concept of anyons, particles that exist only in two dimensions and exhibit statistics that are neither fermionic nor bosonic. These exotic particles could be the key to developing topological quantum computers, which are expected to be far more stable than current models. By exploring the quantum Hall effect in larger systems, researchers are not only refining our measurement standards, but also unlocking new possibilities for next-generation technologies. As we continue to push the boundaries of what's possible, the quantum Hall effect serves as a powerful reminder of how deeply quantum mechanics is woven into the fabric of our reality. Its applications in precision measurement, material science, and quantum computing are just the beginning. By observing these effects on a larger scale, we're opening up new avenues for innovation and discovery, bringing the mysteries of the quantum world into the practical realm of everyday technology. Quantum squeezing is a fascinating phenomenon where scientists manipulate the inherent uncertainties of quantum systems to gain precision in one observable quantity by sacrificing precision in another. At the quantum level, particles like photons or electrons don't have fixed properties. Instead, their characteristics are governed by probabilities. This is encapsulated in the Heisenberg uncertainty principle, which states that certain pairs of properties like position and momentum can't be precisely measured simultaneously. Quantum squeezing allows us to reduce the uncertainty of one property by increasing the uncertainty in its complementary partner. Think of it like redistributing the fuzziness of a quantum system to gain a sharper focus on something specific. Traditionally, quantum squeezing has been studied in microscopic systems, such as single atoms or photons, under highly controlled laboratory conditions. But recent breakthroughs have shown that this effect can be achieved in larger, more complex systems. For instance, researchers have successfully demonstrated squeezing in macroscopic objects like tiny mechanical oscillators and even large ensembles of atoms. This is a significant leap because it extends the realm of quantum mechanics into the world we can more easily observe and manipulate. By cooling these systems to near absolute zero and carefully controlling their interactions, scientists can coax them into a squeezed state where the uncertainty in one property, like the position of a mechanical oscillator, is dramatically reduced. The implications of macroscopic quantum squeezing are profound, particularly in the field of measurement. One of the most promising applications is in gravitational wave detectors, like LIGO, where squeezing is used to enhance the sensitivity of the instruments. Gravitational waves are incredibly faint ripples in spacetime, and detecting them requires measuring displacements smaller than a fraction of an atom's width. By implementing quantum squeezing, researchers can reduce the noise in these measurements, allowing the detectors to pick up signals that would otherwise be buried in uncertainty. This has already led to the detection of previously hidden gravitational wave events, opening new windows into the cosmos. Beyond astrophysics, quantum squeezing has potential applications in quantum computing and communication. In quantum computers, squeezed states can be used to encode information with greater precision, reducing errors and improving computational efficiency. In quantum communication, squeezing can enhance the security and reliability of data transmission by minimizing noise in the signal. These advancements could revolutionize technologies ranging from cryptography to medical imaging, where precision is paramount. Perhaps the most exciting aspect of macroscopic quantum squeezing is that it blurs the line between the quantum and classical worlds. By demonstrating that even large systems can exhibit quantum behavior, scientists are challenging our understanding of where the quantum realm ends and the classical world begins. This not only deepens our grasp of fundamental physics, but also paves the way for new technologies that harness the strange and powerful effects of quantum mechanics in ways we're only beginning to explore. As we continue to push the boundaries of what's possible, quantum squeezing stands as a testament to the ingenuity and curiosity driving scientific discovery forward. Quantum non-locality is one of the most mind-bending aspects of quantum mechanics, defying our everyday intuition about how the universe works. At its core, it describes a phenomenon where two particles become entangled, meaning their properties are linked in such a way that measuring one instantly affects the other, no matter how far apart they are. This connection happens faster than the speed of light, challenging Einstein's theory of relativity and our classical ideas of space and time. Often referred to as spooky action at a distance, quantum non-locality has long been studied in the microscopic world of particles like photons and electrons. But recent experiments are pushing this phenomenon into the realm of everyday objects, revealing just how deeply quantum weirdness is woven into the fabric of reality. In groundbreaking studies, scientists have successfully entangled larger objects, such as tiny diamonds and even mechanical resonators, which are small devices that vibrate at specific frequencies. For example, researchers created entangled states between two diamonds separated by several feet. By carefully controlling their environment and interactions, they demonstrated that the vibrations of one diamond could instantly influence the other, even though there was no physical connection between them. This isn't just a laboratory curiosity. It shows that quantum entanglement isn't confined to the microscopic world, but can manifest in systems we can see and interact with directly. The implications of this discovery are profound. If entanglement can occur in larger, more complex systems, it challenges our understanding of cause and effect, suggesting that space and time might not be as fundamental as we once thought. Instead of being the stage on which physical events occur, space and time could emerge from deeper quantum processes that we don't yet fully comprehend. This idea has sparked new theories in physics, including approaches that attempt to unify quantum mechanics and general relativity by redefining the nature of spacetime itself. Beyond theoretical implications, quantum non-locality in macroscopic systems has practical potential. Entangled states could be harnessed for ultra-secure communication networks, where information is shared instantaneously between devices regardless of distance. This could revolutionize technologies like quantum internet, enabling unhackable data transfer and real-time coordination across the globe. Additionally, entangled systems could lead to more precise sensors and measurement tools, capable of detecting minute changes in their environment with unparalleled accuracy. What makes these discoveries so exciting is that they blur the line between the quantum and classical worlds. By demonstrating that entanglement isn't just a property of tiny particles but can emerge in larger systems, scientists are opening up new possibilities for exploring the fundamental nature of reality. It's a reminder that the universe is far stranger and more interconnected than we ever imagined. And as we continue to probe its mysteries, we're likely to uncover even more surprises that challenge our understanding of how everything fits together. Quantum superfluidity is a phenomenon that seems almost magical, a fluid flowing without any friction, defying the resistance that slows down ordinary liquids. This occurs when certain substances, like liquid helium, are cooled to temperatures near absolute zero, allowing their atoms to behave as a single quantum entity rather than individual particles. In this state, the fluid can flow endlessly without losing energy, climb the walls of its container, and even escape through the tiniest of cracks. For decades, this behavior has been observed in microscopic systems, but recent advances are bringing quantum superfluidity into the macroscopic world, where its effects can be seen and studied on a much larger scale. Scientists are now exploring superfluidity in systems like ultra-cold atomic gases and even certain types of crystals. For example, researchers have created Bose-Einstein condensates, a state of matter where atoms are cooled so much that they merge into a single quantum wave that exhibits superfluid properties. These condensates can be manipulated to form vortices that spin without losing energy, a clear sign of frictionless flow. More astonishingly, superfluidity has been observed in thin films of helium at scales visible to the naked eye, challenging our understanding of where quantum effects end and classical behavior begins. The practical applications of quantum superfluidity are as groundbreaking as the phenomenon itself. In energy transport, superfluid materials could revolutionize the way we transfer electricity and heat. Imagine power lines that lose no energy to resistance or cooling systems that dissipate heat with unmatched efficiency. Superfluids could also lead to the development of ultra-sensitive sensors capable of detecting minute changes in temperature or magnetic fields, opening up new possibilities in medical imaging and environmental monitoring. One of the most exciting prospects is the use of superfluids in quantum computing. The frictionless flow of these materials could help maintain the delicate quantum states needed for computation, reducing errors and increasing processing speed. This could make quantum computers more stable and practical, bringing us closer to solving complex problems that are currently beyond the reach of classical machines. What makes these advancements so remarkable is that they show quantum effects aren't confined to the microscopic world. By scaling up superfluidity, scientists are revealing the hidden quantum nature of the universe at levels we can interact with directly. It's a reminder that the boundary between the quantum and classical worlds is far more porous than we once thought. And as we continue to push the limits of what's possible, we're likely to uncover even more ways that quantum phenomena shape the reality we experience every day. The future of macro-quantum effects is brimming with possibilities that could redefine how we interact with the world around us. Researchers are pushing the boundaries of quantum mechanics, striving to observe these bizarre phenomena on increasingly larger scales. Already, experiments with superconducting materials and specially engineered nanostructures are revealing quantum behaviors in objects visible to the naked eye. For instance, scientists have observed quantum entanglement, a phenomenon where particles remain connected regardless of distance, in systems as large as tiny diamonds. This breakthrough hints at a future where quantum effects could influence everything from communication networks to energy systems. One of the most promising areas of research is quantum coherence at room temperature. Traditionally, quantum effects like superposition and entanglement require ultra-cold environments, making them impractical for widespread use. However, recent advancements in materials science are bringing us closer to achieving these effects under everyday conditions. Imagine a world where quantum computers operate without the need for massive cooling systems, or where quantum sensors embedded in your smartphone could detect minute environmental changes with unparalleled precision. The potential applications of macro-quantum effects extend far beyond technology. In medicine, quantum-enhanced imaging could allow doctors to see inside the human body with unprecedented clarity, detecting diseases at their earliest stages. In transportation, quantum materials could lead to frictionless vehicles, reducing energy consumption and revolutionizing the way we travel. Even in agriculture, quantum sensors could monitor soil health and crop conditions in real time, optimizing food production on a global scale. What's truly exciting is the possibility of discovering entirely new quantum phenomena as we scale up our observations. Just as the discovery of superconductivity a century ago transformed our understanding of physics, uncovering quantum effects on larger scales could unveil principles that challenge our current theories. This could lead to groundbreaking technologies we can't even imagine yet, from energy sources that harness quantum fluctuations to communication systems that transmit information instantaneously across vast distances. As we continue to explore this frontier, the line between the quantum and classical worlds will blur further, bringing us closer to a future where quantum mechanics isn't just a fascinating scientific theory, but an integral part of our daily lives. The journey to this future is just beginning, and every discovery brings us one step closer to unlocking the full potential of the quantum universe. What we learn in the coming years could reshape our understanding of reality itself, opening doors to innovations that once seemed like the stuff of science